So, I'd like to thank the advisors again for inviting me to give you a brief introduction of Cuda Fortran. And this should be really easy because fortunately Dimitri has already done my work. He's introduced Cuda C and Cuda Fortran. You should think of Cuda Fortran just as Cuda with a Fortran syntactic sugar on top. There really is essentially no different. It just has a different syntax. So this should be actually quite easy. Just to briefly review some of the points that Dimitri brought up. Programming GPUs isn't really that hard, as long as your application is amenable. I'll mention a little bit more about that in slides to come. It's ideal if calculations can be made on one datum, that's a singular of data, right? For example, one element of a very large array can be performed in parallel with all other data with very little synchronization. And that's often the case in loop-oriented codes. So the standard paradigms, for example, OpenMP, pthreads, and so forth, don't really express the GPU type of parallelism very well. Therefore, other paradigms have been introduced, for example, Cuda and Cuda Fortran. Okay, what do developers want? Well, this is my take. I'm also a developer. Perhaps you have different priorities, but they want to continue programming in their language of choice. They want, if they have access to GPU machines, which in fact most of you probably do at this point, for example, your laptop, you want to have support for GPUs in that language. The code, it would be nice for it to be portable, and of course you want good performance. So, the step from Cuda C to Cuda Fortran, it's simple. Like I say, it's just syntax. The Cuda kernel is the equivalent of a Fortran subroutine with some additional attributes, which I'll talk about in a second. The attributes, like I say, additional attributes to impose qualifiers on variables, functions, and subroutines. Then there's a one-to-one mapping with the type of things which Dimitri already explained. For example, C qualifier global, host version and device version, or host or device, and there's equivalent attributes on the Fortran side. Show you how to use those in a second. Similarly, he introduced the thread ID, the block ID, in other words, the grid, the definition of the grid, and the definition of the block, and then the ID within the thread block. And there's corresponding derived type to describe exactly the same thing in Fortran, with this time with a %, which is the Fortran syntax for derived types, right? So one-to-one equivalence, just a slightly different syntax. So there are some niceties of Cuda Fortran, and it comes from the fact that arrays are described, I have a meta description, it's called a dope vector in Fortran parlance, which defines several things about the array, and that can be used to describe attributes of that array. Now, why is that interesting? Well, in C, you have to perform an explicit CUDA mem copy to copy data from the device to the host, or in this case, host to device or device to host. And in Fortran, the equals operator is overloaded, so you can do that directly in with the equal sign. That can be done because you have this meta description of the data. This has to be defined as a device vector, and this is defined as a host vector. So, but you can also use an explicit memory copy operation. There is CUDA mem copy, but in general you don't need to. And the launching of kernels are absolutely identical, except it's a subroutine. A kernel is actually defined as a subroutine, so you have to put call in front of it. Okay, so kernel loop directives. There are directives in Cuda Fortran, so somehow a high-level description of how to map a loop onto the GPU. So this is somehow describing, oh, this is a doubly nested loop, and you want to have this blocking, these blocking dimensions and some sort of default grid dimensions for this loop to execute it on the GPU. But if you want directives, you should actually use OpenACC, which I'll talk about in the subsequent talk. So basically, in my mind, you can ignore this feature from Cuda Fortran. Okay, so here's a simple example, a kernel like Dimitri introduced, very simple to add two vectors together, right? And as you notice, there's no do loop in here. Dimitri already presented this. The core is assigned some sort of ID from the thread index, a combination of thread index and the block index. And that core works on that individual datum, right? So Cuda Fortran, exactly identical, right? Except there's an offset, one-based numbering, as opposed one-base indices versus zero-base indices. And the same basic operation. Essentially the same thing, like I say, with a Fortran syntax. Okay, so here is a fairly simple example. You have a main program and some sort of module which contains various numerical operations. And this one here is just an increment function. It increments a vector, A, by some scalar B. So every element is incremented by this scalar B. And even if you don't know Fortran, it should be pretty logical, right? You have an allocatable array, which is then allocated with length n, ignoring the fact that 256 is too small for GPUs for the time being. All of A is initialized to 1. The increment is 3. Therefore, after this increment function or subroutine, all the values should be 4. And we can test that. So, how would you implement that in Cuda Fortran? Well, it's really quite simple. Here, the same subroutine. And then with very few additions, in fact, Dimitri went through this procedure already for another example. You have to add an attribute, in this case global, version on the host and the device. B should be passed by value. In Fortran, it's automatically passed by reference. So the value keyword was added because when you invoke this kernel, you're going to want to pass some of the arguments by value, right? Along with the invocation. You can do that for a limited number of values. And then we need to calculate the thread ID for the particular core, which is executing this operation. Very simple, right? The do loop has disappeared, and now every core is numbered with some sort of thread index. Okay, how does the host code look? And again, same version of the host code. And it's, again, very simple. You have to include a module for Cuda Fortran. There is a device keyword, which obviously implies that this variable, this allocatable integer array, is defined only on the device. That's allocated, right, along with A on the host, A underscore D or underscore device on the device. And we move those over. This is the equivalent of a CUDA memcopy to the device. We execute the kernel or invoke the kernel, again with the same chevron syntax, which is in CUDA C, and then copy it back from the device to the host and test to make sure everything was calculated correctly. Okay, that was a super simple example. I hope I've proved to you that it's really essentially the same as CUDA C, but just with a Fortran-like syntax. We did an extensive case study with not only Cuda Fortran, but OpenCL, which perhaps some of you have heard about, but we won't mention here. And there, in this icon dynamical core, what that is, it's not very important. It's a solver of atmospheric dynamics on the sphere. There were loops, triply nested loops like this, one after the other. Same format with slightly different loop limits. Okay, well, OpenCL version is much like a CUDA or a CUDA Fortran version. It has, it sets the indices, now using a three-dimensional, well, 2 dimensions for the grid and 1 dimension for the block. And there's just an if statement to know whether the core for a certain datum should be activated or not. If it's not, if the if statement is not fulfilled, if it's not in the right limits, then it's ignored, it's deactivated, and otherwise that particular core calculates its index and then performs the subsequent calculation, which is in here. Well, that's OpenCL, and Cuda Fortran is essentially the same, but with a Fortran-like syntax. So again, we calculate, here we have a 2-dimensional decomposition of the thread block, and then a 1-dimensional grid. And then there's a big long if statement to find out whether the core is active or not. And then if so, then it does all the subsequent calculation. Okay. This is probably too small to see, but the code consists, like I say, of triply nested loops like this, one after the other in the code, to very long code, several hundreds, actually thousands of lines of code, not very clean. And so that we split into a kernel invocation, so exactly one of these subroutines, which corresponds to a CUDA kernel, right? And we filled that subroutine with the content, essentially the inner loop here. There was some bookkeeping before the kernel invocation, calculate various indices and so forth. Kernel invocation with the grid dimensions and the block dimensions, and then this kernel is executed, like I said, big if loop, if statement inside here to decide whether this calculation should be performed on the individual code. No more do loops. Okay. I'll just mention some results from this case study. These descriptions define the resolution of the problem we're looking at. Basically, you only need to know that from here to here, you quadruple the number of elements or degrees of freedom. And again, from here to here, it's a quadrupling of the number of degrees of freedom. Okay, and here are results on a wide array of architectures. We're very lucky at CSCS to have numerous architectures to play on, numerous platforms. And I'll just point out a couple here. This is our production platform, an Interlagos node, AMD. It's a Cray XE6. And we have jumps of approximately 4 in time, 23 seconds for the low resolution, 112, a little bit more than 4, and then again a little bit more than 4. And then we ran the Cuda Fortran code, which I just introduced, on a Tesla card. This is a relatively old GPU, and we were very happy to see that this was more or less a factor of 3 faster than our production platform. Well, it didn't end there. Obviously, in all these versions, there were possible optimizations. We then tested it on at that time, a relatively new architecture called the Sandy Bridge, which I'm sure you know. And again, a quadrupling of the times. However, the Sandy Bridge was very competitive against the Tesla card, right? So we investigated some other things. Actually, the fastest card we had was a GTX 480. This is a relatively old GPU with very small memory, so we couldn't run our high-resolution case. However, it has extremely fast memory, and thus the best time of any of the cards. There were some other results with the OpenCL version. The Cuda Fortran at that time didn't fully support the NVIDIA 3.5, and therefore that was not the best performance. However, the OpenCL did perform fairly well on the Kepler card. Okay, that was just a little bit of a case study. Let me just give you the overview of Cuda Fortran. So it supports almost all of the CUDA abstractions you heard from Dimitri's talk. And for example, coordinating threads, organized into thread blocks. Same concepts. For example, shared memory, which Dimitri didn't talk about, and I won't talk about either. Barrier synchronization. There's similarly a sync threads operation in Cuda Fortran. And then thread blocks, as Dimitri mentioned, are independent and they're organized into a grid, can be executed in any order. Subroutines can have various attributes, for example, global, to make them GPU kernels. The allocate is overloaded to be able to allocate device variables, as is the equals operator in order to move data from the device to the host and back, and instead of CUDA memcopy. And can automatically translate some loop constructs to kernels, but I would avoid that, and for the reasons for which come in my next talk. And kernels can be mixed with normal subroutines. So you can have all your old Fortran code and then a couple of modules which include the kernels you want to run on the GPU. It's a very powerful feature in my mind. Chevron syntax still exists. In spite of the compiler developers' attempts to get rid of it, NVIDIA wanted to keep that. Okay, some opinions. It has some strengths. The integration of classical Fortran and GPU-capable Fortran is the key one for me. It's just CUDA, but with a Fortran look, if you like. It has similar performance to CUDA. There's no reason to expect it to perform less well than CUDA C. It has some weaknesses, again, my own opinions. It doesn't really reduce the CUDA programming complexity since it's the same paradigm. Possibly OpenACC, you'll hear in my next talk, might be a more high-level paradigm. It's not portable. It's only supported by PGI. And 2-3 years ago, that would have been a concern for me. However, in the meantime, NVIDIA has bought PGI, so you can be sure that Cuda Fortran will exist as long as there are GPUs for HPC. Okay, that's the end of the Cuda Fortran introduction.